Hi everyone, this is the video presentation of our paper named Data-Driven Solution Portfolios. And this is joint work with Marina, Drygala, Silvio, Lattanzi, Andreas, Maggiori, Svensson, and Sergei Vassilvitskii. So our work falls into the broad area of data-driven algorithm design. And usually the motivation in this area is that companies and practitioners repeatedly have to solve similar instances of the same problem every day. Right, so a lot of works in this area are trying to utilize patterns that may arise in these applications and use them to design tailored algorithms that are provably more efficient when facing future inputs that exhibit these patterns. And efficiency for this presentation will be referring to the running time. So a lot of works have tried to do this for big combinatorial problems. So for example, people have tried speeding up greedy for submodular maximization, speeding up the Hungarian algorithm for computing bipartite matchings. This was later extended to speeding up primal dual algorithms for general graph problems. And people have also tried warm starting various max flow algorithms, and lately also speeding up Bellman-Ford's algorithm for computing shortest paths. All of these works are either problem specific or algorithm specific. So with our work, we wanted to define the simplest problem agnostic framework under which people can use data in order to be more efficient on computing solutions for future inputs. So I want to build up to the framework we define, through an example. So suppose that we are operating some maps application, and there are two specific locations in a city, and a lot of customers are querying for a shortest path between these two specific locations at various times throughout the day and at various times, days in a year. So the naive thing to do would be that every time we get a query for the shortest path, we just look at the traffic, we run Dijkstra's algorithm, and we return the shortest path. Of course, our experience with real-world traffic tells us that the solution to this problem is hardly going to change, and is probably going to be one of maybe two paths. So maybe the least distance path is good when there is no traffic, and maybe in peak traffic conditions there is some alternative path that is perhaps good. So using this prior knowledge that we have about traffic, we could pre-compute these two paths, and then instead of rerunning Dijkstra every time that we get a query between these 2 points, we could simply look at the realization of the traffic, evaluate the two solutions that we have pre-computed, and reply with the best one of the two, right? Yeah, so the algorithmic question is how to identify these two paths, right? So for every future instance, the cost of our selection is going to be the minimum of the costs of the two paths. So essentially, we want to pick these two paths so that we minimize the expectation of the minimum of the two costs, right? And so this objective is pretty fundamental, and it arises also in applications other than speeding up algorithms. So one interesting application is sports betting. So you can fix any contest that you like. So here I have picked NCAA's March Madness. And so for events like this, there are usually betting pools that operate as follows. So you can pay a fixed price to enter the betting pool and submit a prediction for all the matches of the bracket. If your prediction is correct, then you win the amount that has been gathered in the pool, which in real life betting pools is usually a couple of millions. So let's say that someone wants to burn $10 in this betting pool. So the algorithmic question is, what is the best way to spend my $10? And again, if I have a few entries, right, I'm gonna get the reward of the maximum of the entries, and each reward is just an indicator random variable times the money in the pool, right? So I want to pick my predictions so as to maximize the expectation of the maximum of these random variables, right? And after having formulated this problem, we realized that another group of researchers in the 90s had also arrived to an effectively equivalent formulation from a totally different perspective. So in the 90s, companies would mail you catalogs with their items in order to advertise them. And of course, companies cannot print a personalized catalog, or could not print a personalized catalog for every customer because this is too expensive. But instead, they could pick a few catalogs that perhaps are good for different parts or different types of customers. And then for each customer, they would mail the catalog that is closest to their interests. Okay, so again, the benefit that each customer would get is the maximum of the benefits of the selected catalogs, right? And if we aggregate over the customers, our optimization problem is to pick the catalogs of items so that we maximize, let's say, the average over the customers of the maximum of the catalogs. So this is the same objective function as before. So now that we have seen all of these applications, let's formally define the problem. So we call this a portfolio optimization. And this is going to be defined for any combinatorial problem P. In our first example, that was finding a shortest path between 2 points in a graph, right? So this problem has some set of feasible solutions that remains fixed. So in our working example, that was all ST paths in the graph. And we will also be given some set of value functions. So a value function maps the solutions to values and essentially captures all the different scenarios that we might have. And in our first example, that would be maybe different edge weights for the graph, right? So we are also given some distribution over the value functions, and this captures how likely each scenario is to happen. And finally, we have some parameter k, which is how many solutions we want to compute. And our output is simply going to be k feasible solutions for the problem, and this is what we call a portfolio of solutions. So now what is our goal? We said that for every instance, the cost of our selection is going to be the minimum of the costs of the individual solutions, right? And we want to see how this behaves on a new instance that is sampled from this distribution over value functions. So essentially, we want to select S1 through Sk so that we minimize the expectation of the minimum of their costs, right? Equivalently, for maximization problems, you want to pick the solutions so that you maximize the expectation of the maximum of the values, right? And the benchmark in this problem is going to be the best portfolio of the same size. So we're going to say that some portfolio is a C approximation if its cost is at most C times opt, or equivalently, its value is at least C times opt, where opt is the cost or the value of the best portfolio of size K. Okay, so this is the general formulation of the problem. Now we're going to instantiate it for a very simple problem that gives us a very clean question to work with, but still preserves the core harshness of this objective function. So we're going to work with linear maximization over Matroid constraints. So in this problem, we will have some ground set of elements, and the solutions are simply going to be subsets of these elements that have cardinality at most R. You can also think that solutions can be independent sets of some underlying matroid. If you don't know what a matroid is, you can simply ignore this for now. And we're going to look at the case where the elements take values either 0 or 1, and the value functions are additive. This means that the value of a solution is simply the sum of values of its elements. And we're going to look at distributions such that each element takes value 1 independently of the other elements with some probability, right? So essentially, we have a ground set of independent Bernoulli random variables with different activation probabilities. We want to pick subsets of these Bernoullis, right? Every time we pick a subset, the value of this subset is a random variable that is the sum of the Bernoullis. And we want to pick our subsets so that we maximize the expectation of the maximum of these random variables that we formed. Cool. So our main technical result in this paper is that we give a constant approximation for this problem that runs in time that is polynomial in both the size of the ground set and the size of the portfolio, and also works for any matroid constraints beyond cardinality constraints. But in this presentation, in the next few slides, we're going to focus on uniform matroids to make things simpler. So let's make some observations about the problem. So the first thing to notice is that we need to be careful and not take elements too aggressively in all of our solutions. So why is this? Consider the following example, where I have included x1 and x2 in all three of the subsets that I have picked. So the problem that we might face in this scenario is that whenever x1 and x2 fail to achieve a high value, so maybe they're both 0, they will compromise all of the solutions of our portfolio at the same time. Ideally, we would want to diversify and maybe have solutions that do not include x1 and x2. And even when x1 and x2 have value 0, they still have some probability they still have some other elements that are independent, and they have some probability to yield a high value, right? Of course, there is a trade-off, right? Because maybe x1, x2 have extremely high probability of being active. So it could be that this compensates for the problem that they create. But understanding this trade-off quantitatively is not very easy. So one naive way to bypass this would be to simply restrict ourselves to disjoint solutions, right? So what if we try the following algorithm? We just take the subset of the ground set that has the highest expectation, we remove it from the ground set, and then we repeat. We take the next highest expectation subset, and so on, right? So sadly, this approach doesn't work. And the reason behind it is very simple, right? We might very quickly run out of valuable elements. So imagine the following instance. We might have elements that either are active with probability 1 over R or with probability close to 0. So they're practically never active. And from the high probability elements, we might only have enough of them to fill log K independent solutions, locate these joint solutions, right? So we prove in our paper that instead of filling up the rest of the solutions with the useless elements, one could naively just form new solutions by sampling elements uniformly at random from the valuable elements. And this actually will yield a portfolio that has an exponentially better value than using the lower value elements. So it's clear from this example that a potential algorithm needs some filtering rule. So we need to filter out some useless elements. And we also need some mixing strategy, like a strategy that combines various solutions in order to form new ones, right? So any logical filtering algorithm should sort the elements in decreasing order of their probabilities and take a prefix in this order. So we should be biased towards selecting higher probability elements. So this is actually good news because there are only n prefixes of the ground set. So instead of trying to figure out a complicated rule to filter out elements, we can simply try all prefixes, create n portfolios, and after we have created our portfolios, we can estimate their values by sampling the Bernoullis ourselves. We can do this to a satisfactory degree by only taking polynomially many samples. And then we can simply keep the best one of the portfolios, right? So in other words, we can forget about the filtering rule. So what about the mixing strategy, right? In the previous example, we did uniform sampling. And it's natural to ask whether this approach can work in general, right? Maybe in the previous example, it only worked because all of the items had equal activation probabilities, right? And intuitively, you would think that if I have vastly different activation probabilities, maybe I should bias myself towards picking elements of higher probability. Surprisingly, we saw that uniform sampling always works. So we proved that there always exists a prefix of the ground set, so a subset of the ground set, where uniformly randomly sampling your solutions will yield a portfolio that is nearly optimal. So having these two ingredients, our algorithm now is the following, right? So we're going to sort our elements in decreasing order of their activation probability. And then we're going to go through all prefixes of this order and create a portfolio for each one of the prefixes, right? So now, I'm starting with the whole prefix and with the whole ground set, and then I'm going to look at the smaller prefixes. And every time we simply uniformly randomly sample an element with replacement until we have picked at most R elements for every solution. So we do this for the first prefix, we repeat this for the next prefix, and so on until we have n portfolios. And in the next step, we simply estimate the values of the created portfolios, and we can do so with polynomially many samples. So once we have estimated their values, we can simply pick the best one of them, and we guarantee that this is going to be a constant approximation of the optimal portfolio. So how do we analyze this algorithm? There are two main ingredients in the analysis. So the first one is that we are able to find an upper bound for opt. That is the expectation of the maximum of some very specific but independent binomials. And this serves as our target for the rest of the analysis. So we are trying to compare ourselves with these independent binomials. So in order to analyze the value of the portfolio that we create, right? Of course, it suffices to prove that for one prefix, we can yield a nearly optimal portfolio, right? So we look at the specific prefix, and crucially, we first fix the randomness of the instance, and then we analyze the value of the portfolio over the internal randomness of the algorithm. So so we first fix, let's say, a realization, so the 0, 1 values, and then we look at what is the expected value of our portfolio over the sampling randomness, right? So since we are sampling solutions independently, right? Each solution that we sample is a binomial random variable, and all of them are independent of each other. So then we are by a specific conditioning on the randomness of the instance, we are able to show that these independent binomials can be comparable with the independent binomials that upper bound opt, and this way we can prove that the portfolio we create is a constant approximation of the optimal one. So let's wrap this up. So our main contribution is conceptual in this paper. So we formalize the portfolio optimization problem, and we saw that it captures a lot of interesting applications. And our main technical contribution is that for the case of 0, 1 values and independent activations under matrix constraints, we give a constant approximation, right? So now regarding future work, I think there are 3 main avenues. The first one is to extend our result beyond 0, 1 values, but maybe still for product distributions. So it would be interesting if one could design portfolios for the case where each element takes its value from any arbitrary distribution. And the second direction is to relieve the other assumption that we make, that the values are independent, but maybe still we can work with 0, 1 values and relieve the independence assumption. And finally, it would be interesting to also design portfolios for other combinatorial problems, like shortest paths that we discussed in the beginning, maybe knapsack or traveling salesman tours, etc. So that was a short presentation of our paper. I hope you enjoyed it, and thank you very much for your time.